Today we are going to be talking about balancing equations. So the first reaction that we all know of is a synthesis reaction. We all know that a synthesis reaction is a reaction between a metal and a nonmetal to create an ionic bond, or the formula A plus B equals AB. So, as an example, we can get sodium, which is Na, plus chlorine, which would be Cl2, would equal, not really equal, but would create combined sodium chloride. So this is what a great example of a synthesis reaction will look like, but in the following the rules to get this to be balanced, we got to balance it. So we notice that we got our reactants, we got our products. So on the left side of the equation, we could put Na and Cl. On the left side, we have one sodium and two chlorine. On the right side, we have one sodium but one chlorine. So we need to make sure that these two are balanced. So to solve this, we use coefficients and subscripts. So coefficients are numbers you would put before the equation to make the equation more, like add to the equation. So for this example, it'd be 2 NaCl. So then it would go 2Na, 2Cl. So now we have two chlorines. Now it's balanced, but it's not completely balanced because there's not a second sodium on the reactant. So you do the same thing. We got another coefficient here. Make it a 2Na. So now you have 2. So now we have 2 on each side of the equation. So now we proved that it's balanced. Also, sodium is an alkali metal, so it is a +1 charge. Chlorine is a nonmetal gas that is in group 17, so it would be a -1 charge. And when you combine these together, it gets a neutral charge. That's what we want. Same with here. It's a +1, -1 equals out to 0. So now we know that these eliminate each other. If we were to go by valence electrons, it would be the same thing. Sodium is an alkali, so it's in group 1, so it only have 1 valence. Chlorine has 7 valence electrons because it's in group 17, which would get you 8 electrons, which follows the octet rule. Also with the synthesis reaction, this is also used in real life. Sodium chloride, which is this equation, is also salt. So you know that salt is in the ocean. Salt is in a lot of the foods we eat and liquids we drink. And it's in some minerals, and it's also things that are in our everyday life. You see salt everywhere. In every day, we should say that salt is seen or at least noticed. But sodium and chlorine, when they combine together, it creates sodium chloride. We're missing one other thing. Sodium is a solid, so the correct equation for this would be 2Na S. So this means solid plus 1 Cl2, which would be an aqueous. And then the arrow, you get NaCl, which is your salt, but it is an aqueous. And the reason it's aqueous is if we're going to say how solubility chart or go to a solubility chart, chlorine, to make it a solid, you need silver, lead, and one other element, and it does not contain sodium, so that makes this aqueous. We're on to our next bond reaction, which is decomposition. Decomposition is the separation of a bond, which the bond would be AB, and it separates the elements to two separated elements. So the example we're going to be using is hydrogen peroxide. And the equation for hydrogen peroxide is H2O2. And this arrow identifies the separation between this bond right here to give you H2O plus O2. So this would be an example of the separation or the decomposition of bond, which would be this. But we are going to identify this real quick. This is hydrogen, this is oxygen, hydrogen, oxygen, oxygen. Now this is another great example of how we can practice the law of conservation of mass, which we would draw this little box here. We get reactants on the side, products on the side. Basically we put H and O, or we'll just do this, H, O, O. And we got to figure out how many on each side of the equation. So we know we have 2 hydrogen on the left side with 2 oxygen on the left side. So we can put 2 and 2. On the right side, we also have 2 hydrogen, but we have 3 oxygen. So the way we can solve this is we use coefficients as we did on the first one. So coefficients go before the element, and they add that many elements to the equation. So for this one, to make it even, you put a 2. So now we have 4 and 4. So for every one of these, it adds one of these. So if we have H2 and we get a coefficient of 2, it's just H2 plus H2 to get H4. But it would still stay H2, but it's H2 plus H2, then O2 plus O2, giving you more hydrogens and oxygens. On the right side, there would be a 2 right here. Now we have 4 hydrogen and 2 oxygen. And right here, we already have 2 oxygen, so we can still get 4. So you would put a 1 here to identify that you don't need to change how many oxygens are on the right side of the equation, because you already changed it here. We are also, hydrogen peroxide is used in cuts. It's also used to clean up specific items. So hydrogen peroxide is a great germ killer, and it eliminates a lot of the germs. But this separation right here is when you add light. So when you put hydrogen peroxide under light, or pour it into a cup and expose it to light, it will separate to water and into oxygen. So then this will deform. And that's why you see hydrogen peroxide in a black container or a very, very, very dark shaded container. We also have to make sure it's balanced when it comes to charge, and balanced when it comes to the octet and duet rule. So on the left side of the equation, we have 2 hydrogen. We know that hydrogen is in group 1, so it has 1 valence and a +1 charge. Oxygen has a charge of -2, and it has 6 valence electrons. So we know we have 2 nonmetals. So that would make it a covalent bond, which means they share electrons with each other. So if they share electrons, hydrogen has 1, and they share it with the oxygen. So this would have 8. And the oxygens would share 1 back, making these guys have 2. But we're not going to worry about the hydrogen, we're just worrying about the oxygen hitting 8. But we also have another oxygen, so it would also share. This next one's a little more difficult because it's just a bigger equation, but don't let the equation or how big it is freak you out. The next reaction we are going to go up against is a combustion reaction. So combustion reactions are any reactions that are very quick, like thermal reactions between gas, as an example, like lighting gas on fire would be an example of a combustion reaction. But the official, what you need to know that you have a combustion reaction in the equation is you need to have O2, which is oxygen. You need to have H2O, which is water. You need to have carbon dioxide, which is CO2. You need energy. All of these combined is what can get you a combustion reaction. But every one of these has to be in the equation to get this reaction. So, an example of this we'll do this reaction, which so far on the left side of the equation, CH4 is methane, and methane is a type of gas or a natural gas that is underground that we farm out, and we put it into gasoline in our vehicles. O2 is applied as in it would apply to wood, and this O2 in parentheses would be a gas. CH4 is a covalent bond, so we don't need to identify it quite yet. On the right side, we got H2O plus CO2. CO2 is an identical gas, and this is a liquid, so we can identify it as a liquid in a gas. CO2 plus H2O, and then plus energy. So now we have everything in this equation to solve it as a combustion. We have our O2, which is here, our H2O, which is here, CO2, which is here, and then energy, which is here. But specifically, this is thermal energy because the bond is basically lighting a piece of wood on fire. But this is how you light methane on fire, is with an equation like this. But first we have to balance it, following all the coefficient rules that we've applied with the last two equations. So we will set up the chart over here. We'll set it up a little better than we did last time. This is the best way to write it out. So let's put C, H, O, which are our three reactants. We have 1 carbon, we have 4 hydrogen, and 2 oxygen. On the right side, we have 2 hydrogen, we have 3 oxygen, and we have 1 carbon. So instantly you know that carbon matches up, but you see hydrogen and oxygen don't match up. So this is where we get to have fun and play with some numbers to solve which ones or which coefficients can solve out the rest of the problem to make it an even equation that we can call balanced. So we'll start off with 2 oxygen with 2 H2O. And the reason I'm doing that is because I'm trying to balance the oxygens first. So on the left side, we have 4 oxygen. And we get 2 oxygen, but we already have 2 oxygen over here, so we get 4 oxygen. And we also need to add on to the H2O, so we also get 4 hydrogen. And so we can put 1 and 1 because we balanced this properly. So now, this is what you would call balanced, because there's an even number of elements on each side of the equation to make it a completely even reaction. So now we need to draw, I'm going to draw out to explain also how we make sure this is all balanced following valence electron rules. Yeah, so we'll start off with CH4. So carbon has 4 valence electrons, and there's 4 hydrogen, and we know, since this is covalent, the hydrogens and the carbons share electrons. So the carbon will follow the octet rule, because for the 4 hydrogens that are here will make this carbon an 8 charge, which follows the octet rule, which the octet rule is having 8 electrons here to make sure it's balanced, which would make this a balanced equation. For O2, it's just 2 O's. O's have a charge of 4, so each one of these represents 2 that it shares. So these oxygens are sharing, or these represent 1, and the oxygens are now following the octet rule, but there's 2 of them. So we have 2 of these bad boys, which makes both of these work. So now let's move on to H2O. H-H-O. These 2 share, which makes this 8, follows the octet rule. Let's go to CO2. C-O-O. These both share 1 here and 1 back. So since we have 2 oxygens that are equal to 6 valence electrons, and this carbon's 4, that means these will represent these as 2 electrons that share. So this gets to 8, and this shares 2, so these get to 8. And it means this is an even, we're doing this correctly. And then all this would be plus energy, which then starts the reaction that we need to light the methane on fire, or turn it into fire. Looking at combustion reactions, we're looking at if it's stable. We're looking at if when you combine all these together, it works. So to tell if this is stable is following the octet and duet rule, as I've been stating. So as we see here, the 4 hydrogen and the carbon, when they share electrons, covalent bonds share. So I can put this as well, that covalent equals sharing of electrons between these, and the oxygens are already sharing, so that means they stay even, and same with these 2. So that's how we know that this is stable, is if all of the elements in the equation follow this process, and it follows the process of staying even, and also having an even valence electrons between all of these. We also are looking for how do you use this in real life, right? So you get your methane, which is here, oxygen, which creates water, carbon dioxide, and energy. So basically this process starts the flame, and it burns. It burns the wood. And that's what the reaction is you use this method right here to burn anything when it comes to adding methane with this, and you can tell that by it's a correct combustion reaction by this, this, and this. Alright, this one is single replacement. Single replacement. The equation is A plus BC is equal to B plus AC. That is the magical equation. Single replacement is the switch between two bad boys, which we got the A and the B because of reactivity. So the A comes in, B comes out. You can see that it came out and they switched because the A is more reactive than B. That's why the switch occurred, is A has a higher reactivity than the B. Example of this, we got potassium plus some H2O, arrow, line, then we got KOH plus H2. So this right here is potassium hydroxide. Potassium hydroxide is a specific substance that I can explain later of what it actually is, what it's used for. But we need to balance this out first using the rules that we've been applying lately. Potassium, we're going to start off by doing valence and electronegativity levels. Potassium has a +1 as one atom. It has one single atom out of all the valence electrons it can use. But since it's by itself, it has a charge of 0. Because any element that's by itself has a charge of 0. H2O, hydrogen has a charge of +1. Oxygen has a charge of -2. You have two of them. So it's +2 -2 gets 0, and hence they're HO, they're nonmetals, which would make it a covalent bond, and that means they share electrons. Hydrogen will share 2 of their electrons with oxygen to follow octet rule, and it'll be charge neutral because -2 + 1 + 1 would give you 0. So we so far know that both of these are stable elements. Potassium hydroxide, OH here, this is a coefficient. Not a coefficient, a polyatomic. A polyatomic is an easier way to identify specific elements, and it lets you know of the name used. Hydroxide is a -1 charge, which is convenient enough because potassium is a +1 charge, which make this balanced. But since we have a metal, non-metal, non-metal, or a metal and a polyatomic, the polyatomic combines with this, so we get KOH. So this is the transfer of one electron, and these share to get 8. So this is how you identify. So this has 8, follows octet rule, charges +1 + 1 -2 goes to 0. And then this is a 0 charge because it's by itself, as we explained with the potassium. It doesn't matter if it's metal, non-metal. And hydrogen has 2 hydrogen, so it shares and follows the duet rule, which would make all of these stable. Now we have to follow one more rule to know if this is completely balanced. So we are going to make the chart. We get reactants here, products here. You get KOH. You have 1K, 2H, 1O, 1K, 1O, 3H. So now we got to balance this bad boy out. So we get an even number between both sides of the equation here. So we'll start off by, we're going to add 2 to KOH because we need more H. We can put this at 1 because we want to put this to 4 because we can put 2. So we get 4, you get 2OH, then 2K. So then you have to mark this as a 2. You get 2. You already have 2H2O, so it's a 2. Now this is balanced because there's 2 potassium, 2 oxygen, and 4 hydrogen on each side of the equation, which explains we've done everything we possibly can to prove that this is an evenly balanced equation. The stability here, we can explain why it's stable. We get K. Bonds with K. This is a metallic, except they're running around. Because potassium is both of them are metals. So since it's a metal plus metal, it's a metallic bond. So with these 2 electrons, the electrons are running around like crazy, like faster than me. And you get your 2 hydrogens with the oxygen. It is a covalent bond, so that means they share electrons. So the hydrogen and the oxygen share. So they follow the duet rule because this shares 1, while the hydrogen shares its 1 to the oxygen, which makes it 8, which that is the octet rule. And that's what we want. So we know that these 2 are stabilized. So now we get KOH, which is right here, and they bounce, this shares or transfers. So potassium and oxygen, it transfers its 1 to get it to here. The hydrogen and the oxygen are already sharing because it's hydroxide, so they're already sharing, they're already happy there, but the potassium transfers it to here, to this, to give you the octet rule. The last one, H2, which is hydrogen, they're both 1, they're sharing because they're both covalents, so +1, it's a +1 because it's in group 1, but it is not an alkali metal. Make sure you remember, hydrogen is not an alkali metal, even though it is in group 1. So hydrogens are sharing, so you follow the duet rule of 2. So it's 2 electrons for a duet and 8 electrons for the octet rule. Potassium hydroxide, which is this right here, it is used in shampoo and it is used in products. That's why we have H2O. So this reaction occurs when you add it to a liquid and creates this, which it makes you smell good. The reactant is to kill germs, and that is why this reaction does take place. And because the hydrogen here has a lower reactivity than a potassium, so that's why the switch does finally occur. And that is the explanation of what a single replacement element is. Reaction of 5. This one is a double replacement. So the last one we did was a single replacement, which was the change of one element that has a higher reactivity with the other element. This one is a little bit different. Equals a D plus BC, or CB. Either one works. But this is when you have a higher reactivity with one of them, with the A, and it works better with here. Now reactivity that's lower is these 2, which still make up 2 bonds, 2 different bonds that also create a stability. So the example that we are going to be using is we're going to start off with one that we started off with at the beginning also. We get our sodium chloride right there, plus little line for coefficients when we get to it. Then we get our silver fluoride. Then now we get to the product side, which now we get a sodium chloride plus, we didn't draw a little coefficient line for this one, but we will, plus a silver chloride. Now, what's one thing we can notice about this very quickly is all of these are ionic bonds. Sodium is a group 1 alkali metal. Chlorine is a group 17 gas. Silver is a transition metal, and fluorine is also a nonmetal gas. And then we get over here, sodium, fluorine, group 1 alkali and a gas with a silver, which is a transition metal, with chlorine, which is a group 17 gas. Now we know ionic bonds. So how do we solve an ionic bond different from a covalent bond of stability? So we'll start off by showing how do you get a stableness between all of these. So sodium has a charge of +1. Chlorine has a charge of -1, which will give you 0. With valence electrons, it would be also 1 valence electron with 7 valence electrons. And instead of sharing, the sodium transfers the 1. So then that's why this is a +1 and a -1. It is the chlorine receives the electron from sodium, which makes this out, and chlorine follows the octet rule. Let's do it for silver and fluorine. We get Ag and fluorine. So here's a little difference here. Silver is a transition metal. So since silver is a transition metal, we got to figure out what is the charge of fluorine, which is a non-metal in the right side of the periodic table. Fluorine is a -1 charge. So to make this equation work, silver then has to be a +1. And now we have the balance. Fluorine, and then when we come to valence electrons, it works a little different. Fluorine would have 7, and then silver would give away 1 due to the ionic transfer of electrons. Now let's go to the right side here. We get sodium, which is a +1, an alkali metal, fluorine, which is a -1, which balances out. Conveniently enough, it gets 0, that's what we want. And if we go correctly, sodium has 1 valence electron, fluorine has 7, equals 8, follows the octet rule. So that means this is stable, and that is stable. Now we get silver chloride. Chlorine's a -1. And since we marked on the left side that silver's a +1, we will also mark on this side that's a +1, which gives us 0. And the chlorine has 7. That means the silver would have 1 still, which follows the octet rule, which means all 4 of these, everything in this problem, is stable. And we don't need to mark coefficients because they're all 1. I don't see any subscripts. So that means it's all balanced. And now we balance the equation to the fullest of extent. To part 2, which is more explaining on double replacements. So now we're going to see the solubility between all of these, which we should have done a lot earlier. So we'll start off with, we know that Cl, we can figure out how soluble Cl is. So chlorine can only be soluble to 3 different elements. And they have to be either silver, lead, or Hg, which I can't identify the specific element in my head. But we know this is not one of the 3 that is supposed to be it. So that means this right here is an aqueous, which is soluble. Now we'll go to the next one, which is silver fluoride. So silver fluoride is just a little bit different because we can't identify it as a soluble insoluble type of bond between each other, but we can identify that it is a solid because silver is the solid. Now on the right side, we can identify sodium fluoride. So that'd be NaF. So we have a metal non-metal reaction, which would give it solid. Now we're on to the final one, which is silver chloride. We know that chlorine is soluble to our magical thing of silver. So, since it's not it is a soluble reaction, it would make this a solid. So this one, the sodium chloride and the silver chloride, are both soluble solutions, but this is an aqueous because it does not contain the three specific elements we need to make it that. So sodium chloride, as again in the real world, is used as salt. We already talked about it. A silver fluoride is used, it's a compound of silver fluoride, yeah. And it's basically just like a thin substance of silver to identify specifically if you have true 100% silver. Sodium fluoride is also a specific type of element. It is also a type of poison. They use it as a poison. It's also in drinking water and toothpaste, but the poison, it's used for rats. So it's not going to kill you. And the most soluble, this is the most soluble in water. It's very, very high soluble in water, we should say. And then we finally get to our silver chloride, which is used to identify specifically if you got let me restart this because I explained this very, very, very poorly. This is used in real life to create like a crystallized form, and when it signals silver, so when you have a piece of silver, it'll turn it to like a grayish, blackish, purplish color to identify that you have the correct color. It's also used when you add heat to it. You can also identify the silver inside of this. We explained how balances worked. We explained all of that to make sure that these equations for double replacement correctly substantialize that it's even. And you can identify the solubility of all this because this right here, the chlorine. You can also have the chart as well. Since we have a metal, non-metal, ionic, even though all these are ionic, we know that chlorine is a solubility, or it has a soluble chance, and they're both soluble or aqueous until you add the element to it. Do we have anything else that we need to cover? Thank you for listening, and that is the difference between the 5 reactions. We covered the synthesis reaction, we covered the decomposition reaction, we covered combustion, single and double replacements, and these all can be identified. We'll just clarify A plus B equals AB. AB equals A plus B. This one you need CO2, H2O, O2, and energy. Single A, B plus C, and then A plus BC. It can also be screwed around. You can mix it with it. It's just that's one of the ways you can write it down. And double replacement is AB plus CD to AD plus BC. These are equations that are good to write down, and it will save you a bunch of time writing these down because you can solve or figure out any type of reaction that occurs with just these equations. So thank you for watching to my explanation of the 5 reactions.